So maybe I can say that we would want to classify, right? We would want to classify, means we want to know what are all, and this discussion will be quite incomplete. Okay, meaning that I won't call the previous discussion incomplete because you can fill in the things, or you can easily read because the language is built up on what you have done. But this thing might be taking a few steps.
So
Yeah,
one second.
right.
So actually, I have some stargazing thing at 9:45, so I'll have to leave now.
Oh, okay. That's fine. That's okay. Yeah,
Okay.
yeah.
Yes. So next class we'll meet, which is Saturday, right?
Uh, yes. Yeah, Vaishnavi, Saturday, are we meeting? Saturday morning? Or
Saturday morning at
fine?
8:30.
8:30. Yeah,
Yeah.
8:30. Yeah.
Yeah.
So come
Saturday.
along at 8:30,
Okay.
then we can see. 8:30 a.m., okay? No,
8:30 a.m. Yeah.
a.m., okay. All right. Okay. I hope that is
Okay.
fine.
Yes.
All right,
Yes.
no
Yes.
problem.
8.
Okay,
Okay.
no issues. Yeah.
Yes. Thank you, sir.
Okay, no problem. Yeah. All right. So let's see. So basically, we would want to classify locally compact non-linear spaces, right? Because see, what you have seen just now is that, so if I have a non-linear space, right? So it is locally compact if and only if the unit ball is compact, correct? That is what we just saw, right?
Yes.
That if the unit ball, so you have a non-linear space, if the unit ball is compact, then you show that it is locally compact. And that is same as saying that closed and bounded sets are compact. All these three are equivalent. You can still take it as an exercise and try to prove, right? Given a non-linear space, if the unit ball is compact, then it's same as being locally compact, and it is same as being same as saying that closed and bounded sets are compact, right? All these three things are same. But now we would want to ask which non-linear spaces are locally compact, right? So that's the question. Which non-linear spaces are locally compact? Yeah. So we have already seen that all finite dimensional nonlinear spaces are locally compact. That's what the very first thing we did, right? All finite dimensional ones are locally compact. Or basically just saying that the unit ball, the closed unit ball is compact. But then the main theorem is, which I think I will not prove, but I will give you the idea. And I think you cannot complete the proof on your own. But if you can, then that will be great. But without reading, I think completing the proof of this will be a little challenging. But still, nonetheless, let me tell you the idea, and it's a wonderful idea, and that's one of the things. So the theorem is, okay, that is that if B10, this is a unit ball, and basically this is usually written as B, but yeah, this closed unit ball is compact implies that non-linear space V is finite dimension, right? So try to absorb this. Try to absorb this. Try to see how this is sort of a nice result. So if you have infinitely many directions, right, then even inside the unit ball, you can, construct a sequence which does not have a convergence sequence. And that's because you have infinitely many directions, because you have because the dimension is infinite. So basically, I mean, I'm saying basically the contrapositive, right? That if V is infinite dimensional, then the unit ball is not compact. Okay. 1 minute. So, right. And I'm just looking, right? So you can see the result. Yeah, there is another definition, and okay. Yeah, there is a completely, and that's the magic. There is a proof which is I actually don't know this. I've read this proof, but okay, I should not read it right now. Okay, right, but the idea I will tell you that's based on a different, based on a different thing. So you understand, right? So what we will just prove is, okay, I mean this way, yeah, that if V is not finite dimensional, then the unit ball is not compact. Okay, so what will I prove? Okay, we'll actually prove that. So maybe I'll assume, I will not prove this, I'm sorry, I'll just give you the idea. Okay, assume that assume V is, I got it, that's called the Riesz Lemma, right? The Riesz Lemma is the key. Okay, now I understood, because I was thinking Banach, it's not Banach, it's Riesz Lemma. Somehow, yeah, it implies something for something called Banach spaces, which are the important non-linear spaces, but the lemma is called the Riesz lemma. But yeah, and this is the hard lemma. Okay, yeah, but somehow there are. But yeah, let me tell you something which is useful first. Useful, but so what we'll do is like this. You assume that V is infinite dimensional, or I'll just say not finite dimensional. Okay, right? We want to prove that, right? So we want to show, maybe, right? Want to show that B is not compact, right? We want to show B is not compact. So we want to show, but this is more in the spirit of having infinitely many dimensions. So I'll write that right now. And that this will imply that it is not compact, but this is the correct thing to show. We want to show that there exist these infinitely many directions. Okay. These are basically like directions. Okay. That there exists these things, yeah, such that in fact these will be on the unit ball. Okay. So you can understand, right? If you have infinitely many directions, that's really the spoiler. Is it spoiler? No, I don't know. That's really the, yeah, that's really what leads to the loss of compactness. But how? Yeah, I can only draw 3 dimensions, I suppose, but yeah. So you have infinitely many directions such that what happens? How do you ensure? So what is this? This is a sequence, right? So the idea is that you have a sequence and you want to show that the space is not compact. So what would you show? Such that this xi, what should we show to show that it is not compact? Has no Cauchy subsequence. If it doesn't have a Cauchy subsequence, it cannot have a convergence subsequence. Doesn't even have a Cauchy subsequence. Okay? And this is the, I gave the homework, I suppose last time, that if you have a totally bounded set, now totally bounded was a concept we talked about. That also is something which, these are the exercises of real analysis, right? That show that a set is totally bounded, which the definition I've said, you can just look at it. If and only if every sequence has a Cauchy subsequence. That's same as being totally bounded, correct? That is an exercise of analysis which you should do. It's very easy to prove. Or if you try it and then you try to look at that book. It's easy. Okay? That is basically what we are bringing here. That characterization, if you have done that exercise and if you kind of living, like it's there in your subconscious, is there, right? If it's there, then you will know that this is what you should be doing. Has no Cauchy subsequence. How will we show this kind of thing? How will we show this kind of thing? More and more concrete than this. We will show, because I mean, eventually if you want to show something, it will be something more. You always show something a little bit more. I mean, if you are doing a constructive proof, right? I mean, whatever, it depends. But yeah. Such that xi mod xi, I mean, how do you show something is not Cauchy typically? Or right, it doesn't have a Cauchy subsequence, it's kind of spread out. And because these are sort of directions, because these are sort of infinite directions, you know that you know that these directions are what is leading you to construct this kind of sequence, right? So you will show that this is bigger than or equal to half for all I and j. Okay, now forget all this. Just try to show this as an exercise and analysis, right? That if you have a sequence, for which this property is satisfied, then it cannot have any convergence subsequence, any Cauchy subsequence. Forget convergence. It cannot have any Cauchy. That's an analysis exercise, right? All these things you have to do, but you do them, then you can you appreciate this. This is what we will show. This is what is shown in the theory. And to show this, we use the Riesz lemma. And what is the Riesz lemma? It's a very beautiful idea. So what is that idea? The idea is like this. Now I'm giving you the idea. Phone, no, not in the middle. Right, yeah, that's fine. Okay. I mean, this is optional. Yeah, no problem. Yeah. Okay. So the point here is that the idea is that if you take any closed subspace, if you just think that if you take any, yeah, okay, that's fine. That's all. Yeah. So if you take any subspace, yeah. Oh, yeah. Okay, yeah. Okay. Good night. All right. So if you take any subspace, right? So what do I want to show? Right. I want to show that there are there is this kind of sequence. There is this kind of sequence. So how will I show that? I'm trying to tell you. Yeah, this is like why do I need a closed subspace? Yeah, because yeah, because that's not, yeah. But now look at the idea. The idea is that if you take any closed subspace, okay, right? Or just I mean, you probably don't have to worry about closed subspace. Just think about a finite dimensional subspace. Yeah. Why did I say that in the beginning? Because I mean, I'm also somewhat new to this stuff, this thinking along the way. Yeah. You just need a finite dimensional subspace. So the idea is this, that you look at What should be a notation for finite dimensional subspace? I don't want to call it F because F is a bad notation. Yeah, maybe V naught, right? Or VI, right? So VI, you look at VI in this, and dimension of VI is finite. Okay. So V is this infinite dimensional space, right? I mean, that's what we are assuming, right? That's really the key. V is this infinite dimensional space, but we are saying that if you have any finite dimensional space, subspace, then look at this finite dimensional subspace. Obviously, this is not everything, and that is really the point. That's the meaning of infinite dimension, right? Which we are going to use. Because this is not everything, you know that there is a vector W, there are many vectors W. There is a vector just a bad name I want to give so that because it's not going to be important. There is vector T outside. There is some other vector. There are many vectors which are outside, with all of them having norm 1. Yeah. So do you agree that such vectors will exist? Right? Such vectors will exist, right? With norm 1, which are not in this space.
Yes.
Because there is a vector outside the space and then you can always scale it. But there is not one, but there are many. I mean, because it's infinite dimension, you can do that, right? So the point is that among these vectors, there is a vector which is perpendicular. We don't have a notion of angle in our space, unfortunately. But if you've done linear algebra, you will see that you can introduce notion of angle in inner product space and so on. But unfortunately, here you cannot introduce that notion all the time. That's a non-thing, but you can still sort of imagine, right? That there is a vector which is sort of far, means in the sense that there are many vectors which are of distance 1. Among all the vectors which are at distance 1, among all the vectors which have norm 1, there is a vector which has norm 1, but it is sort of further apart from this space Vi, right? Kind of a perpendicular vector. Okay. So you see, this vector will be the key to our problem. Okay. This kind of vector will be the key. Why? Because if you can prove that such a vector exists, I mean, what is such a vector? I have also not defined. I've just said, that it's far apart. All of them, we are only talking about norm 1 vectors, but among those we are talking about the one which is far apart from your Vi, from your given finite dimensional subspace. And what does that mean? It means that there is a small epsilon, okay? Epsilon is greater than 0, but it is small, okay? Or, I mean, why do like that? I should tell you from the context, such that distance of this vector, there is a vector Vi, small vi, such that distance of Vi from capital Vi is more than half. This is what I am talking about. Vi has norm 1, and this property is satisfied. Okay, and distance of a vector from a space, it means that I'm just saying that given anything here, the distance is more than half. Or you can just say that even the perpendicular distance is more than half, but there is no such perpendicular, so you have to say like this. Okay, I am saying you want this kind of vector. Okay, you want this kind of vector. Okay, and if you have this kind of vectors, then you can feel like intuitively that inductively, if you produce these vectors v1, v2 like this, then this sequence of vectors will do this job. So do you see this intuitively, that this is this kind of sequence, if you produce like this, which is geometrically motivated like this, then it will do the job? Is that something that is that I have been able to say? No? Yeah, yes or no? Like because
Yes, yes.
right, you understand the intuitively, right, that this is the idea, right, that this sequence of vectors will do the job. Obviously, we are still far apart. Yeah? But now there's something which I can give you for a homework, and there is something which is difficult, which I will not give you for homework. What I can give you for homework is this. And that is again just an exercise in metric space and analysis. And if it is wrong, then you can tell me, report back. So the exercise is, okay, that given v1, v2, dot with vi norm equal to 1, right, such that distance of, and you can investigate this concept of distance of a vector from a space as well. Distance of vi plus 1 from vi is greater than half. And what I mean by this small vi, this is just the span, right? This is just the span. Okay, right? If you have this kind of sequence, which so you understand. So you take I and then I plus 1, and then you take that I plus 1 also form vi, capital Vi plus 1, and again Vi plus 2 has a property. So it's sort of an inductive definition, right? There's also something kind of things which are very convenient in mathematics. Also obviously in computer science. Yeah. But this, then that implies that Vi has no Cauchy subsequence. And basically, Vi will have this property is what I'm asking you to prove, basically. Vi has no Cauchy subsequence. Right? Is it okay?
It's
Okay. So this, I think once I write it, it's kind of, I mean, at least to me, it's almost obvious, but obviously that doesn't mean anything. I mean, if I already know something, then it will be obvious. Yeah. But you have to take it as an exercise and see. Okay. And basically, this lemma is a special case of what is called the Riesz lemma. Riesz is you should read about him. I mean, I'm not saying should, but just that I like to read about the mathematician sometimes. Yeah. Okay, this is missing, and then you see the wonderful fact, right, that this is something is finite dimensional if and only if it's locally compact, right? That's the game. That's a very beautiful. And then from here, all the functional analysis sort of kicks in. Okay, and yeah. So look at it, and maybe let me just share. Maybe I can see if I can tell you. If I can look at the proof of the Riesz lemma and maybe see if you can read it later on. Yeah, it would be there in some book as well, but unfortunately yeah, okay. You see, it's a lemma in functional analysis, and it specifies conditions that guarantee that a subspace is dense. Yeah, I mean, I did not go into that way. That's the problem. When you read this, then you have to read what is dense and read all that. And yeah, and this is, you see, this is what I was saying intuitively, right? That if you had an inner product space, which is sort of, if you had a notion of angle, then that lemma which did the job, that would be obvious, because you can just take the orthogonal vector which is orthogonal to that subspace, right? Take a vector which is orthogonal to your subspace. Then any vector with norm 1 will also have distance 1, because it's 90 degree. You can sort of think use and sort of intuitively, right? Yeah, but the Riesz lemma, the way they state is y is a closed a little bit. I stated a simpler version of finite dimensional, but they will say a lot of things. Yeah. subspace of a norm space, then alpha be any real number. This was my sort of epsilon. Okay. Then there is a vector with norm 1 whose distance from your space is always bigger than this 1 minus. Okay, so this is not epsilon, it is 1 minus epsilon. This was my 1 minus epsilon, and this was my distance. Correct? Yeah. This is the same, but obviously different places will write it in different ways. Okay. Yeah. And yeah, this you don't reflexive space is sort of little advanced for the time being, but the proof can be found in this book and this. Yeah, so I suppose you can read the proof. And no, there are some. Yeah, they don't have the proof here. Yeah. You see the consequence, right? Infinite dimensional nonlinear space contains a sequence like this, and so in plain English, these vectors are separated simultaneously, all lying on the unit sphere. Such infinite vectors cannot be found in the unit sphere of any finite dimensional space, and so yeah. And this sequence can be, this is what I talked about, and this can help you to characterize finite dimension, and this is a proof of that fact, but it's sort of more abstract. It's difficult to understand right now, but soon you will understand it. So what can I tell you? Let me see. It's possible for you to read it. I think it's a little difficult. They use some things. I mean, and you see there is no thing that you have to read it today only, but still. Yeah, it's very simple. So please read this, okay? Please read it, and you can tell me next time. It's a very small proof.
Okay.
Okay. I mean, reading, see, it's not like when we are in high school, it's like, reading is what mathematics is, not for reading, it's for doing. But here you see, when you read, you actually have to do. Otherwise, you cannot really read, right? I mean, this is okay. So reading should not be considered as, oh, why is just reading? Where are the problems? No, reading is really doing the problems. Yes, think about it. If you read it actively, and if you don't like, if especially the proof is not telling you everything and you have to fill in the gaps, then reading is really, yeah. Anyway, I'm telling you that you should read it, and you can see where the link goes. It's just this proof. You can read the book, but in the book it might be a little I mean, where it is and whatnot. I mean, is that maybe so? Yeah. If you read this, then I can sometime later, when you're more comfortable with topology, you can go into this. But right now, yeah. But the point is, what you should understand, that these lemmas, which are sort of, you can understand how they are, right? Basically, see, there is a structure, there is a space where it has a lot of structure. There you have some consequence because you can use the structure, but you would want, like for example, if you're in a space which has angles, then this is trivial. Okay, but still you should think those spaces are called Hilbert spaces. But yeah, but the point is that angle notion it will be fine. But what I'm trying to say is that the notion of angle gives you a consequence, but that consequence remains true even without the notion of angle, right? So even without the structure, the consequence remains true, because the structure leading to the consequence was because that was a logical path to get to the consequence. But the consequence might be true in general, and that's the point. So this is the example of that, where the consequence is true in places where you don't have the notion of angle. And then to come up with these lemmas is really the art, right? Coming up with them. Proving is not really difficult. If you look at this, you will see that the proof is not impossible. If you sit for long enough, you can prove. I mean, in the sense that, yeah, but coming up with it is really, knowing what to prove is really very important. Okay. So yeah, so you can think about it. Maybe, yeah, then we can talk about other things later. Okay. Is that fine?
Okay.
Right?
Yeah.
So this way you can get into the game, because slowly functional analysis is something which you should try to look into, because doing linear algebra you're doing, and functional analysis is just linear algebra, but you have infinite dimensional spaces. Yeah. So I think that's it. Let's stop here. We'll meet on Saturday. Okay. All right.
Okay.
Okay then. Bye. Bye.
Bye.